The overall problem is that we have loads of data points scattered about. Some of them we have labels for, and some of them we don't. So in this case, like blue is a label and yellow is a label. And we want to assign labels to the other points. And you can kind of see the best way to assign, well, the way that you can think of as of assigning labels is say, well, if points are close to the yellow ones, we want them to look yellow. And if points are close to the blue one, we'll assign them as blue. So the first question is, how can you do that in a numerical way? And this is where the graph p-Laplacian comes in. So just to illustrate it, here's my example. So in this picture, these big points here have been assigned a label. So that's like the yellows and blues, but this time I've got lots of different colors. The rest of the points, I haven't got a label for them yet, and I need to assign them. So the method that you use is called the graph p-Laplacian, and basically what this does is it penalizes if two points are close to each other and have different labels, then the value of the overall function with all the labels is high. So it makes points close to each other have similar labels. So here, this is using gradient descent to try and find this optimal choice for the labels. And you can see, like up here, near this blue one, everything's gone blue. Down here, everything's gone red. So it's great. We've already got our problem solved, so why am I here? Well, the problem is that when you have a large number of data points, this graph p-Laplacian becomes more and more expensive. And if you've got n data points, then the expense scales like n squared. So it gets very large quite quickly. The good thing is that somebody has found that if you take the limit n to infinity, then you can go from this discrete version of the p-Laplacian to the continuum p-Laplacian. So here's the same situation. These points are fixed, and then I've got, instead of discrete points, now it's a continuum of points. And I run gradient descent in a different format because now we've got a continuum. And what you end up with is another function which determines the value at each point. So you can see around here, there's a trade-off between making the surface as smooth as possible and having this distinct value here. So also great. Also, I haven't done anything yet because someone else figured this out. The problem is that to do this continuum p-Laplacian, to get this continuum p-Laplacian result, you need to know the density of the data. And we don't know the density of the data. If we knew it, then I don't think we'd have to do this at all. We'd have solved everything already. So the question is, how can we approximate the density and still get the same continuum result? So the only thing that we do have is our spread of data points. So I've added a few more here just to make it more visible. So we've got this massive, across our domain, we've got loads of different points. And we want to approximate the density out of them. So the first thing we do is add a little blob of continuous mass around each point. And that'll end up with something that looks like this. This is called the kernel density estimate. And you can see it's got, well, first of all, it's good because we've got a continuum. The problem is that it's nowhere near as smooth as we expect the data to be. So we need some sort of smoothing method to smooth it out. This is called density regularization. And there's lots of other ways to do it. The way that I've focused on is called smoothing splines. So I've made this thing called the Spline-kernel density estimate. And you can see it's a lot smoother now. So the question is, does this converge to the real density? And the answer is yes. We found that it's a very strong style of convergence called uniform, almost sure convergence. So what we're saying is that as you add more and more samples to your data set, the difference between, or the maximum difference between the density estimate and the actual density goes to 0 with probability 1. And also, I've constructed estimates on the error between your density estimate and your actual density. So these are almost sure estimates as well. So how does this fit into what we're doing? The end result is that we want to use this density approximation in the actual Laplacian minimization problem, the gradient descent and everything. And the situation is that we can use it now. And not only can we use it, we've also proven that in the limit, as the number of sample goes to infinity, using our density estimate in the p-Laplacian gets the same result as using the actual density. OK, so I'll hand over to Ollie now. He's going to talk about the other part of the project that we've been doing.
Thanks. So maybe one question that kind of sparks people's minds right at the beginning is, what is this distance we choose to kind of assign points? We said close together, we some kind of distance, but a real question is like, what is this distance? And suppose I've got some points, and here we can see that we've got two classes, yellow balls and blue balls, and currently there's no kind of separation between these classes. The distance we're using to think about these points is not informing us in any way. But there might be another distance in which these two classes separate. So by what I mean is, suppose that there was a way to look at these images, points, and here we have the two classes separating nicely into two different sets. So this could just be two different ways of looking at the same set of points. So what is this? What is this distance we're looking at? OK, there's this formula, but I'm going to go through it step by step. So what I want is a map called T. And I'm going to ask that T is going to push in my case, an image into another image. And that's all it's going to do is rearrange all the pixels so that the first image, when you apply T to this image, is going to be the next one. Now, how am I going to do this? Well, I'm going to tell it that pixels can't be moved very far by this map, right? That's what I mean by distance in this setting. And modulo sum, so I'm asking, I want the smallest map. I want the map that minimizes this distance. And this is called the optimal transport problem. So just to remind you that I want a map which is going to move pixels in an image from one image to the other, and I'm going to ask that it doesn't move pixels too far. And this is a well-defined problem modulo some mathematical assumptions on the map T. And what does this look like? So if I was to think about this image, and I want to move this image onto this one, if I was to do this in a kind of Euclidean way of just seeing how far I was moving, I would chop some of the density off this image and just move it to the other location. I'd walk back, chop off some more, walk back to this thing until I've finished walking back continuously until I've moved my entire image. In the optimal transport framework, I'm going to take the whole mass and just keep pushing it towards the new one. And what we see is the optimal transport kind of preserves some geometric properties of the original image. So why are we doing this? Well, our original problem was to perform image analysis on people with celiac disease, and we wanted to kind of automate the diagnosis of celiac disease. And one of these, the problem we had was, how do we measure distances between images? And we believe that this optimal transport framework would help us do this. So this is the image we have, or lots of images like this. And you ask, OK, what is the distance between this image? OK, there's some pre-processing happening. We convert it to grayscale, and we do some other standard things. But what is the distance between this image and this image in some way? And this image and this image? And what about if we had a load of diseased people? What would be the distance between these images and those? And if you've got really good eyesight, there's a little spoiler, and this doesn't actually work, right? And the reason it doesn't work is you can probably see from the images they're really different, right, in all kinds of ways. These are all from healthy people, and some of them are from the same person, and they're very heterogeneous. There's very much damage to these images down here. There's this kind of muscle mass that goes in here. There's so much heterogeneity in these pictures, these images. There's no hope for us. And with the optimal transport, it's not able to pick out the signal from the noise in this case. So what do we do? So maybe we use a different distance, and maybe this is going to help us. So this is something called the transportation LP distance. It's a kind of higher order distance than the optimal transport. And what it's saying is, I've got my original problem that I had before, right? Everyone recognized this part. Don't move my pixels too far. But I'm also going to say, well, I also don't want to move my colors too far. So this distance actually applies to full colored images. So I'm going to penalize if you move red to blue rather than red to red as well. Good, we hope this works. So far it's been a test because this was proposed in the mathematics literature only 2 years ago. So to gear it up to be worked in applied problems, we have to create something called the linear transportation LP distance, which is an approximate method, but that's all that really matters. We can do this, and we can look at a synthetic example and see if it's actually any better than optimal transport, even in a kind of setting where we should know it should do better. So here, I've just created a bunch of points, simulated them from 3 sets, and here, these are our classes when I look at the optimal transport distance. We see they're quite diffuse, they're quite spread out. They still form 3 classes, but they're still definitely the within class distance is often bigger than the between class distance. And when you move to this new framework, the same simulated data, they form nice, tight clusters. And so maybe this is a better distance to be working in. So where do we go from here? So we need to develop this kind of linear TLP a little bit more, this distance on more simulations, and see how it's performing. It requires a lot more algorithm design and things like that. And we want to apply this to the celiac data, or maybe a summary of this celiac data. We can now create maybe vectors of more information from these images and apply it straight to this directly. And Tim?
Then for the p-Laplacian side of things, we'd like to extend the numerical results to higher dimensions. So the code that we've written is for use on 2-dimensional things. It does generalize, but there is like a curse of dimensionality thing that might happen when you have too many dimensions in the continuum. But there are ways to combat that, and we need to look into that more and see if there's specific situations where it's beneficial. And also investigate other functionals. The methods that we've used don't rely too much on the fact that you're using the p-Laplacian. So what about if we use other functionals that can be used to cluster particles or cluster data points together?
Yeah, thank you.